ओके, मेरी आवाज क्यों नहीं आ रही यार? ओके,
so good afternoon to everyone. We are having Professor Dr. Karabi Biswas among us. She holds the position of Associate Professor in Electrical Engineering Department of IIT Kharagpur. She pursued her PhD in Sensor Development from IIT Kharagpur, her MTech from Jadavpur University, and BTech in Instrumentation Engineering from IIT Kharagpur. Her research areas are sensor development, instrumentation and sensor designing, study of fractional order systems. She is having more than 30 international journal articles, more than 30 conference proceedings in her credit. She also supervised 11 PhD scholars, among which 6 are pursuing PhD and 5 are already honored, and 3 MS students, 1 pursuing under her guidance and 2 has already been honored. So with this, I would like to request Dr. Karabi Biswas to proceed with her present.
Okay, thank you very much for your nice introduction. So I think I am audible.
Yes, ma'am, you are audible.
yes, ma'am.
So I can start presenting.
Ma'am, as per biodata mentioned there in the website, Mr. Chandan introduced you. But if you want to add something more, your achievement or anything, so please, I am happy to know that.
It's fine. Those who actually, I have a personal web page. He has maybe taken from my institute web page. So in my personal web page, some informations are there. So if someone is interested, they always can visit my web page and see. So need not miss anything more. Okay.
I mean, these things are also beneficial of the participants because all participants are from the maximum 95% are from faculty of different engineering colleges across the India.
Okay.
So they are also beneficial. What type of work you have done? Yeah, what is your achievement? So then they can contact regarding any such type of research to you. So if you introduce yourself some more thing, then all of we are very happy.
Okay, that's good. So actually today I will be presenting the topic you have given, that is sensor selection and designing, right? But actually this is my research domain only. I do sensor selection and I do make the instrumentation system. But apart from this, I have actually one more research area that in the last Mr. Chandan has read it, that study of fractional order system. So there actually we are able to build a circuit element which is not a resistor, not a capacitor, not an inductor, but something else. So what is that? That is, if you can understand that, something between resistance and capacitance. Now with this development, actually this was for last 50 or 60 years, people tried to realize this element by combining different resistance and capacitance, but we could make a solid state fractional capacitor, and that gave me many international recognition. Like I am presently now a international management committee observer of the European Cooperation of Science and Technology. I have been actually called by the Russian government to give a plenary talk on the 95th birth anniversary of Roshit Nigmatulin, who actually first in 1940s with the solid state or not solid state, by the triode valves realized the fractional these capacitors. So this is a research area which I won't be talking today. In many places I give talk on the design of that fractional order capacitor and what is its utility and how actually it is brings some benefit to the circuit designer, to the control engineer, to the system identifier. So those who are interested, you can see my website. You will be see there are two distinct class of publication of mine, one in the area of the sensors and instrumentation development, and another is the area of circuit element development, that we call a fractional order element or fractional order capacitor. So but today I will be talking on the sensors part. Okay, so let me start with that presentation, and those who are interested, you can see the website, and if you have any query, if you want to discuss about fractional order capacitor, you can always mail me. Actually I am more comfortable in mail because my phone always remains silent mode, my this cell phone, but I'm frequent in 1 hour at least I check my mail once. So if you have any query, you can mail me and I will be able to try to answer your queries. Okay, so let me present, right, today's presentation. So this will be full screen, is it? No. Why a present window should come, right? Are you able to see my window? No.
No, ma'am.
So I am going to present. Then on this drop box menu, there should come that a window should be presented, right?
Yes, ma'am. Yes, ma'am. Just
But
you find that there is a button for present now.
yes, I have actually, I am conversant to the Google Meet. I have given the present now, and in the drop down menu first came the whiteboard, then change layout, exit. Why the whiteboard came? It should come a window, right?
No, no, sir. No, no, ma'am. Just in the present now, there will be 3 options.
Okay,
Your
okay.
entire
It came.
screen.
Yes, it came, it came. So I will be talking about sensor selection and design. So sensors, you all know that actually human body is the is the best place to find all types of sensor. But if we just categorize, then we can see that there are only this eye, ear, skin, nose, tongue, that actually we have read in our very primary level classes. So when we try to make these senses, so what we want to mimic this whatever they are in our human body. So this eye corresponding senses is actually a camera. That means if I want the vision. So here the corresponding one is the microphone, which is the audio senses. Skin, that is actually touch. We have touch sensitive devices, you know, for the robot design. This is very much a essential element to design a touch sensor. Nose, smelling, and we had trying to develop e-nose. That means many chemical sensors. Nowadays, chemical sensors has come with a big importance. So we had actually the e-nose, not only chemical sensors for the chemical warfare or military applications, but even the food quality or the pollution control. So many places we try to actually develop the e-nose sensors. And tongue, as you know, we are that are test sensors, and we are also trying to develop, people are trying to develop the e-tongue, okay, so electronic tongue. So this is one set of classification, because when we talk about sensor selections, we need to know actually what we are trying to select and what we are going to design. There are thousands and thousands, and even not thousands, actually the billions of sensors available now. So always it is good to have a classification on some basis. So here on the human perception basis, it has been classified, and in all these you can actually make big list of sensors. So in the touch sensors, so you can, your temperature sensors, your pressure sensors, all can come in this touch sensors, okay. So some people try to classify the sensors according to the 6 energy domain, and that 6 energy domain is magnetic, chemical, radiant, mechanical, thermal, and electrical. So why all the pointers are put towards electrical? The basic reason is that nowadays all type of physical variable, we just want to convert it to the electrical domain. And the basic idea, as most of your faculty, you know, that electrical signals are easy to process, easy to store, easy to communicate. So that's why most of the sensors which are previously maybe mechanical, if you can think of that, previously in pneumatic sensors that were when we are students, we used to talk a lot about pneumatic sensors. But nowadays very few industries, they use such pneumatic sensors for pressure sensors. They have developed different type of sensors, small, because pneumatic sensors takes a large area, which is not very desirable, and also other issues are there. So we concentrate on the making, we can sense, we have to sense, we can not can sense, we have to sense from the physical world. So all different types of physical sensors will be there. Then our motto is to convert it to the electrical signal. So if we see a matrix, actually from every domain to every domain, we have the some effect which defines. So suppose if I say radiation to radiation, then the photoluminescence effect is called that the sensor which does this part. If I want the from radiation to mechanical, then the radiant pressure sensors. There is a sensors which is called radiant pressure sensors. If I want from radiation to chemical, then some photochemical sensors we can develop. So similarly, this matrix shows that you can go from any domain of energy to other domain of energy, and you can make different types of sensors. So I think you can see all are different types of name of different types of sensors which are actually based on some physical variable. So from magnetic to electrical, this Hall effect sensor, this is very important now, because Hall effect sensors, the Hall current probe, that is very useful in current measuring. And not only that, actually works on the magnetic principle, so we get many other advantages which you don't get in the capacitive, inductive or potentiometric sensors. So that we work on the Hall effect sensor. So inductive sensors also maybe the magnetic effect, but the Hall effect sensor has some extra advantages because it can measure very small amount of current. So we just, when we want to design, to a design engineer, this matrix should be clear to her or him, that from which domain I am measuring, because what is my physical domain? Because if I am measuring the environment temperature, naturally I cannot measure an electrical signal. I have to measure, I have to make a sensor which can measure the electrical, which can measure the temperature, that means thermal sensors. Then we can convert to an electrical sensor. So maybe by using thermal sensors, so we use Seebeck effect, or there may be others also, just I put that is which is thermography is based on. Okay. So I think this matrix, more or less all the terms are known to you, and you see this basic principle of operation is actually based, you can classify any one of these which is shown in this matrix. So sometimes in broad classification, people now say that there are two classification we can want to say, that is physical sensor and the chemical sensor. So a physical sensor is a device that provides information about a physical property of the system. That's what I was trying to tell, that if you want to measure temperature, or if you measure the displacement or a dimension, so that is a physical property. And the other is that you want to make the chemical change or chemical reaction. So as we have designed, we have categorized in 6 energy domain. Now again, people can classify some of them as a physical sensors and some of them as a chemical sensors. So you will see the biochemist, medical domain, they try to classify according to the physical and chemical sensors. So we all know that this chemical sensor is a device that transforms chemical information, and that means it may be useful for whether particular component is present or whether it is actually up to some level. That means suppose some explosive you want to measure. So that means that whatever that detector does, that any volatile organic compound, that means that is a chemical species is coming out. So from that they measure that that is explosive or not. And so that is only the detection, that whether it is present or not. But sometimes when you have done the experiments in your chemistry lab, when you see the different components you have used, then you have tried to see that whether reaction has occurred. So then after a particular amount is actually added, then the reaction starts. Otherwise, the reaction won't start. So that is also the basis of many chemical sensors, because that particular amount we want to measure. So this is very straight. The chemical information may originate from a chemical reaction of the analyte or from a physical property of the system investigated. This is important because from the physical property, that means the temperature, the pressure, they will also give me some chemical information. That's why the biochemists or the biomedical engineers, they say that when this physical property can be converted to the chemical nature, so I can classify according to this to domain only, physical and chemical senses. And this main issue of chemical senses are identification, that I have explained with the explosive, quantification, that means how much amount is present. So that is quantification, how much amount is present. How I will say, suppose you are trying to, if you are cooking something, let us take an example of that one. So you have seen that in the recipes, they say that you measure, give this amount or that amount, then only it will become good texture, or it will come out with the different colors. So what is that amount? I need to measure in every chemical reaction. So that quantification is also an important issue for chemical senses. And when we go for chemical senses, they are mainly gaseous or liquid phase. Solid chemical sensors are not very common. So that means the chemical sensors that comes out is gaseous or in liquid. That's why you understand the biomedical engineers mostly they want to pathological test and all, that all liquid or gaseous states, and also the biochemists that are gaseous and liquid states. So that's how the classification has come. So I think chemical sensor application, you will see same as a physical sensor application. It can do atmospheric monitoring, pollution control, detection of explosives, characterization of gas samples in laboratory to track the migration of chemical hazards. So you understand all these are actually very important, because this migration of chemical hazards, this is a big issue with this COVID. At the beginning, we are thinking, okay, because lockdown, our environment is getting cleaner and all, so we are becoming happy. But that's we don't want a COVID to control our chemical hazards. Rather, we want some sort of other solution so that this migration of chemical hazard does not take place, right? Now you are hearing this ganges become very clean here and there. So we don't want that some pandemic to do that one. Rather, we want some sort of mechanism so that we can stop this migration of chemical hazards. So in medicine, so naturally this is to detect patient's health, trace gas content in the lungs and in blood sample, and chemical sensors are actually useful to detect fuel pump, groundwater contamination in the military. So in industry also, you will see that process and quality control during plastic manufacturing, production foundry metal, or amount of diffused gases affects metal characteristics, that is brittleness, environment monitoring. Then in electronic noises, test and control food spoilage, distribution of pesticides in agriculture population. So, and to grade the beverages. Why I took the example of the chemical senses, because the physical senses more or less you are aware of, you have read about these senses, but maybe these chemical senses will replace many of our physical sensing property or physical senses in these different industries. So let us take an example of a machine building industry. The question comes, why we talk about sensors and why this sensing is so important. You know, previously people used to say that our first industrial revolution was automation, then came the informization. So automation was started from after the Second World War to up to some 1980s. So after 1980s, the information, now you can know we have lots of information. Whenever any information we require, we just search in the Google, because that is to us maybe the best search engine. So information is the next phase of automation, and the third phase of automation, people say, that will be the sensorization, because you are also heard now people talk about the IoT devices. That is nothing but putting the sensors everywhere. So naturally we wanted to look into that, our conventional machine building industry, what are the benefits we get when we use sensors and when we do not use sensors. So first is, if we use a sensors, then we can get the early fault diagnosis, we can do quality control in a better way, we can optimize the process, because when the reaction will occur, then maybe a color will change. So if I can if I can get that information with the sensor, then actually next time when I will be allowing the two chemicals, then I will allow for that much of time, then I will maybe stop the control valve so that the chemical does not come, because that chemical, if flows after my reaction, that is the wastage. So with the sensor only, I can detect that when the reaction has taken place. So it gives us the flexibility in design. Of course, the comfort, because when you all understand that actually you stay in a air condition or in a industry, so how much dust particle present, how much is the humidity, how much is your temperature, if you can measure that one, then it puts the comfort to you. Okay, and when you do all this, your cost is reduced, we can work for less pollution, that means we can choose among different materials being used, and then we can see which is producing, suppose some gas, hazardous gas is being produced, so NOx or SOx or carbon monoxide. So if we see that the coal, suppose in a coal, there's some sort of different types of coals are there and different sizes of coals are there. If you go to the power plant, you will see. So if we can see that a particular size of coal is actually, it burns in a better way and produces less smoke, then we can actually will go for that particular size. So that's how the less pollution and also many other application can be told. And energy saving, of course, is the now energy is a big issue to all of us, because our fuel will get exhausted, that is fossil fuel. So we are all looking for the new energy sources, so energy saving, because all these operations actually saves our energy. And of course, with this we actually want the increased economy. So that's how actually we try to select sensors that according to my application, according to my requirement, I want to just put these sensors. Even nowadays, the tractors, so is in the agriculture field, which is running, they are also they try to see that which, because all the plants may not have grown in a same way. So there may be some image capturing camera or some sort of sensors is mounted, and they see the height of the this plant. Then if it is up to some height, then only they will put the pesticides, otherwise they'll think that that plant may die. So all these things actually is required for your um, cost or add to your cost effectivity. Now, of course, the question comes that what is the overhead and what is the return. So that is a big question, and a country like developing country like us, so when we want to implement, this is the main issue which comes in our way, that how to actually put the sensor or automation in every field. Because if you see the Europe and America, I think that sensor market is more than 60-65% cases they use sensors, while in India or these developing countries or poor countries, we use hardly 2 to 3% cases we use the sensors. So what will be the census selection criteria? So for different application, there are different census selection criteria, but nevertheless, people have tried to formalize that what will be my gross temperature selection criteria. So first they tell about the temperature and the size, then the protection class. So I'll come on this, what we understand by protection class. So then we talk about whether the sensor requires a discrete or analog input. That means the sensor will work with the discrete signal or the analog input. But most of the, if you want to measure from the environment, then most of them are analog input. But after processing to signal processing, if you make digital, go to digital domain, then there may be also a sensor which may work on the discrete domain. Okay, so sensor repetition, this is what is, that means we want to say that for a particular application whether we can use the same sensors repeatedly. So on that, which sensor I can repeat. So actually if I can repeat the same sensor in different places, that actually gives me this cost effectiveness, because I know its process, I know its, if one sensor's installation is known to me, then for all the other sensors I can do that one. Then accuracy, sensor response speed, and sensing range. This is, I think, known to you. Accuracy is actually true value, may be the difference between the true value and measured value, and in percentage it is divided by the, either by full scale reading or by the measured value into 100. That's how the accuracy is defined. So that is important criteria when we use the sensors. And also the speed, because if you can understand that, suppose the thermometer, the mercury thermometer, when we used to go to the doctors, they used to say that the thermometer should actually, you should put 2 minutes under your arm, so that you get the value of the temperature of your body. But nowadays you see that with this COVID, what people do, that there is a thermal gun which is being pointed to you and they'll see the temperatures. So the response time of that mercury thermometer, if was same or with this thermal gun, then this is of no use, right? So according to the application, we actually need the sensor speed. Now the sensing range. So this mercury thermometer or this thermal gun by which we measure this body temperature, that range may be very small. We know that maybe from 95 to 105 if, or 1010, that range is fine with me. But if you are doing in a chemical industry where you may have to measure maybe the minus temperature. But suppose the cryogenic engineers, they need to measure the minus temperature. Again, they want to bring back the room temperature. That means from some minus temperature to some 50 degrees centigrade. So this hot application you are using, on the basis of that, you need to actually select your sensors. So naturally the question comes, what defines the sensor selections? So as I was saying, knowledge about the application type and basic operation condition. So when identifying the short list of sensors, make sure that the set which meets the basic operating condition of the application. This is very important, the basic operating condition of the application. If it does not meet, however good sensor you are procuring or you are trying to design, that will not work. So the question comes, where the set of specifications are available. So these are available on the manufacturer's data sheet. So you understand that all of you, I think, have used the operational amplifier. That is a very common example. So when you try to use that operational amplifier in a circuit, so what you want to see first, that what is the power I need to give, then what are the pins for my input output, and then you see that at the beginning that what temperature it will work, what is this non-linearity, what is this sensitivity. So everything has been available in the manufacturer's data sheet. So similarly, for different types of sensors, if you go to the market and suppose you are a factory owner and you want to make total automation of your factory, so first you need to know that what I want to do, what specifications I want to meet. So according to that, you actually go to market and procure your sensors. Or rather, if you are an owner, you can give to a design engineer, and to the design engineer should know that what specifications actually will be beneficial for this industry, right? Suppose a medicine making industry, they work on a cold temperature condition. So that cannot be same by steel making industry. So both of them may need the temperature sensors, but that what is a requirement that differs on the applications, and on that basis of that application, if you have to identify the specifications, and you have to if you are going to manufacture, you have to make your own data sheet as an engineer, or if you are going to buy the sensors, you need to understand the data sheet, that what are the specifications. So in a factory automation, already I have told this, that these are the things, but here one thing I have added, answering the question, will it be beneficial to be able to change parameters? If the answer is yes, then an input output link enabled sensor should be considered. That means 1, 2, 3, 4, 5. This 5 I will first look into. Then this is also a criteria, that will it be beneficial to able to change the parameters. That means whether these sensors actually I use, so we'll be able to perform the task to change some parameters. Then if that's so, then I want to give some input, get some output. So that's why the IO link enabled sensor should be considered. So some people have also made some additional requirements for factory automation, that is a response speed, sensing range, repetition accuracy, electrical connection, mounting time. Again, there is an answer to be question to be answered, that is, is on sensor visual display required? Because you'll see that maybe your factory workers, they don't know that how this is moving, what is the temperatures. So they just want to read that on a big display that okay, this is the temperature. So if you put an analog on, or if you put a digital display, whatever it may be, so for your factory automation, this is a as a design engineer, you must have to consider that whether I'll go for a visual display or not, whether it is required or not, because the visual display always requires nowadays people with the LCD. Previously maybe the LEDs are used, now LCD, and the cost of the total component is actually much lesser than the display. So unnecessary, if you put some visual display, then that is not a good engineering design for this factory automation. So I said that what we understand by the protection class, actually this International Electromechanical Commission, they have actually some ratings, okay, and that they call the ingress protection, IP. In that, what does it do? It classifies the degree of protection that the enclosure provides against solid objects and liquids, and also to operate in the enclosed electrical equipment. Because if you are going to select the sensors, then you must know that these sensors, in which environment it will be actually give me the optimum output, and at which environment it will actually deteriorate, how is the lifetime. So there is an International Electromechanical Commission who has defined some protection class. So see, if that is marked as 0, it means there is no protection. If it is marked as 1, then protected against solid object bigger than 50 millimeter. That means hands. That means you can handle it with the hands. So if 2, then the solid object bigger than 12 millimeter. That means you can handle with your fingers. Against solid objects bigger than 2.5 millimeter. That means thick wires and tools. So that means the what you are trying to select for your design, or if you are a design engineer, you are trying to develop a sensor, then you have to actually, after manufacturing or after developing the sensors, you have to declare that in which protection class it belongs to. Is it no protection? Is it protected against solid more than 50 mm? Then you have to put just the number 0, 1, 2, 3. So there are actually different protection classes. So you can see, if you put a 6, that means your sensor is totally protected against dust. So that's how actually this sensor works in our sensor market works. And when the design engineers try to build the sensors or try to design our automation, then we should be aware of all these facts. So this everything is actually available in the manufacturing data sheet, and you must be equipped with to understand this manufacturing data sheet or read this manufacturing data sheet. So let us see that in an automobile. So there are, I think, like human body, a self-driven car is same type of, it has lots of sensors, thousands of sensors. So some of the sensors are actually displayed here. So you can see the indoor, outdoor, seat belt tension, rain sensor. So before this, going to this, just I want to ask if there is any question. So you can interrupt me and ask some question. Is it okay? I'll
Hello.
continue then.
Hello. Hello.
Yes.
What about that?
Is there any question?
What about that ultrasonic sensor?
What is your question?
Ultrasonic sensor, that's an optical sensor in optical field. What are the development till now, new development in optical sensors?
Okay, actually, here you want to say that what is that? I did not talked about optical sensors. I was just saying about how the sensors is selecting and how we should design.
In selection criteria, you are telling that accuracy is one of the factor for selection. In that case, precision must be taken into account. The sensor should be precise also at the same time.
Actually, what you are talking about, that comes when we design the sensors, okay, design specifications. So there are not only precision, there are hundreds of specifications.
Other specifications.
The precision, accuracy, drift, hysteresis, there's non-linearity, so many. And then in the dynamic, we want to see the settling time, rise time. So I am not talking about still about that one. Okay, so I just talking about the general criteria of sensor selection. And if you are asking about optical sensors, I am not a person from optical domain, but my knowledge says that optical sensors are very good when actually we want to do very accurate measurement. Right, so that time optical sensors are obviously should be used. But main problem of optical sensors is actually it is costly, right? And it is costly, and more often actually this optical sensors, the main advantage is that for communication channel there is actually no loss. So that gives us a big advantage. So for communication, we use this optical sensors. But again, this is application specific, I would say. And what is the development that actually those who are doing research on optical domain, they can give you the latest development of optical sensor. And I want to clarify one more thing, that ultrasonic sensor is not same as optical sensors. Ultrasonic sensors are acoustic sensors. Ultrasonic sensors, they actually when we produce a sound wave which is more than the hearing ability of human being. Okay, so principle of ultrasonic sensor is different than the principle of optical sensors. Okay.
Can the conventional sensors are implemented in terms of? I have one question more. Can the conventional sensors are implemented by using optical sensors?
Conventional sensors means what type of sensor you say? We have optical temperature sensor. We have optical pressure sensor.
Pneumatic sensors and hydraulic sensors, can they are implemented?
No. As per my knowledge, not. But I think those who do research, they can talk about it. But for my knowledge, I have not seen the optical hydraulic sensors that is being implemented in optical domain. Okay. So you just maybe there are some, because every day some new thing is being coming up. So you can just look into that, what is the research field. Okay. So okay. So may I continue with this? The sensor in automobile. So again see, when I have that in Indian road, if I have this, I don't need an sensor, or most of the Indian cars, this which with the middle class people buy, they don't have a sensor on the back seat belt. But nowadays everyone has the sensor on the this is a driver's seat, and okay, this car is of right driven car. Okay, this is a driver's seat and this is the occupant just beside the driver. Nowadays you will see that if you do not push a seat belt, then what will happen? This car will not move, it will give a beeping sound, right? So if you go back 5 years back, that feature was not added. So that means there is a sensor put inside this. So if that in that slot the belt, that head does not go and press, that means there is a pressure sensor. Then what is an engine management system? That is a complex control system, consists of all the signals coming from different parts of the car, and then it allows your engine to start. So that is actually nowadays implemented, because front seat now maybe the government regulation is has to this put your seat belt, but in the old cars this feature was not there. And in America and all, if you're in back car also, if you do not put your seat belt, the car will not move. So that means what I wanted to feel that according to the country also, this selection of sensors also differs. Now the coming to the other sensors which are actually nowadays common to every automotive industry, that is accelerometer, that we require, because what is the speed I am going to. And nowadays most of the cars have that airbag that gets inflate when there is an accident, that actually sensed by the accelerometer. We have the oxygen sensor, because the oxygen level goes low, then my burning of that oil will be less and our efficiency will go less. We have water coolant temperature, because you know the most of the car has a IC car engine. There is a 4 cycle. So first cycle is intake of pressure, then it compresses, then it explodes. Small explosion takes place, and that small explosion actually produces the force that actually drive the car or moves the power train of the car. We call that axles and the gears and all. So that we need to do. So when this explosion takes place, the heat develops. So we need a coolant temperature. You know what happened once? I was driving my car and something hit in this front side of the car. So I was going someplace, my car stopped at the middle, and I was totally blank that why my car stopped. And that time heavy rain came. So I was standing in the car. So after rain stopped, then car started moving. Then I came house. Then I thought that must be because that time I did not know about that what happened to my car. So when I went to the garage, the people say that actually your air that coolant that has which actually that has got damaged because something has hit in your front side of the car. So without this coolant, actually your car will not start. So there is a sensor which will actually if I would have a sensor in my car, I would have known that actually this temperature goes high and it is not cooling down. That is the reason the next cycle of engine management system is not starting. So that is an oil sensor. You all of you have seen there is an indicator which gives the oil sensing, rain sensor. We have indoor outdoor temperature sensor. I already have talked about passenger occupancy sensor. We have a fuel level sensor, speedometer. We can have a odometer also. Parking sensors are now very much essential because we have lots of cars and less of parking space. So we want that. And tire pressure sensors, because if one of the tires for some reason get deflated, and if you're going in a very high speed, then what may happen, it may topple. So in the big trucks, that is actually very important. So wheel speed sensors are also there, and of course you will see that anti-theft sensors. Nowadays, if someone touch your car or try to unlock your door, then a beep sound comes. So all these sensors actually come into place. So what I wanted to show that actually your according to your application, the sensor selection gets totally different. Now someone was asking me about the optical sensor. Here, what is the optical sensor we use? Actually, if we will be doing the self-driven car, then the optical sensors are being used to see actually what is the distance between. Ultrasonic sensors are also being used, but ultrasonic sensors, the problem is that according to the environment, it's get affected because this goes through the air. So if it is rainy, it is humid, so that sensor may be okay, but the time of flight, the time it takes to go to the other solid object and come back, that changes according to the acoustics, according to the environment. So that sometimes give less accuracy. So in that case, some optical sensors are being introduced. In the high-end cars, we'll see that sensors are there. So we can say that what are the design criteria for automotive applications. So here you see we need a temperature range from minus 40 degrees centigrade to 125 degrees centigrade or 150 degrees centigrade. So why need minus 40 degrees centigrade? Because we need to cool our air, fuel, that part. And when the exhaust or the explosion takes place, then that produces high temperature. So I need the sensors in the engine to measure that what is the temperature, and that temperature sensor may be different for the people which are sitting inside the car. They are actually, I need some, our body temperature is something around 35 degree, 35, 37 degrees centigrade. So we want something 25 degrees centigrade. So, but here it has mentioned minus 40 to 85 degrees centigrade, maybe because they have thought of the cold countries. So what is the inside temperature, what is the outside temperature, that they want to measure. And all this automatic selection criteria that has to be qualified according to the AEC, that is Automotive Electronics Council. So what I am trying to emphasize here, that when as a design engineer you are going to design or select, you must see the specification manual. And if you are going to be an entrepreneur, then you must know that actually in that domain what are the standard available and which standard I am going to meet. So according to that, we have to lay down our sensor specifications. So we have to pass this production part approval processes also. We have to see that our sensors should able to withstand for electrostatic discharge. this is, I am talking about automotive applications because there are electrostatic discharge takes place, but in inside drug this manufacturing industry, this electrostatic discharge may not be an issue. So we want this electromagnetic compatibility, because you have seen that automotive car, how many different sensors there. So there are so many electromagnetic interference. So at a different parts, there is this electromagnetic compatibility is there or not for your sensors. So when you are selecting the sensor, it should be able to pass that one. So, and also safety and integrity level. So that is also you have to look into. That means for automotive application, if you are selecting sensors, then all these one you have to consider. The failure modes, effects, and diagnostic analysis. This also you have to. That means for different sensors that you are using, you have to see that what type of regulation is there. Said by the Automotive Electronics Council, or this ISO standards, and then you have to go for the car manufacturing or designing the cars. So now IoT has come at a big way. So what about selecting sensors for IoT? So this is a typical part of an IoT. I think all of you know what is IoT is, Internet of Things, and this is actually our sensor. Then there is a local processor, local storage, there is a network system, then there is the internet, then cloud processing, and then the cloud storage. This is the basic block diagram of a IoT. Now, the difference between the conventional sensors and IoT sensor is that it has to actually work with the local processor. Local processor is that, it means the computer, right? So it must to, be able to give the digital output. So that means the sensors which I am making, it must be accomplished, or it must be enclosed with a signal processing circuit which will be giving me a digital output. So naturally the people will think that rather than converting from analog to digital domain, do I have any sensor which directly gives digital signal? Then that will be, of course, an added advantage to us, right? So people select the sensors on the basis of that. So different when you go to the different domain, then different selection criteria actually has been laid down. So now I come to the next part, that is the designing. So all these we need a concurrent and collaborative design methodology for the sensors. So what do we mean by that? Why concurrent and collaborative design methodology? This I will explain with an case study, or maybe with some examples, so that you have a, you can follow it. How much time I have left?
Ma'am, you can continue up to 2 o'clock, ma'am.
How much? Half an hour?
Half an hour, yes, ma'am.
Okay, so fine. Half an hour.
This is up to you, ma'am.
It's fine. I'll be able.
But anyhow, you finish before 2.
Yes, of course. I have to also take lunch, no problem. Okay. So we need a concurrent and collaborative design methodology. So what is the issue of this design methodology? That is, I have to 3 issues I have to meet, and these 3 issues are actually, the objective, what is my objective, what is the principle, and what is the methodology I am going to adopt. That is the issues I need for concurrent and collaborative design. Now, what is this objective means? The objective means to develop the methods and associated component tools necessary for the concurrent engineering design. So, what do we mean? Methods, you understand, that means the procedure by which I will be developing this component tool. I will explain what we mean by the component tool. And concurrent design means actually I will be able to design concurrently the engineering design. Okay. So, what is the principle I have to follow? That is the minimizing the number of components. If I can make a sensor by minimizing the number of components, so that is always advantageous. And nowadays you have seen that automotive, that automobile car. So there are so many sensors, and you don't expect that all of them will be the macro sensors. So we want to go for the micro domain. So MEM sensors are there. So in that, actually minimizing the number of components is very much essential, because unless I minimize the number of components, I need more fabrication steps. This is true for macro sensors as well. So if I want to, I have number of components more, I need more processing, and that actually add to my cost. So I need to develop the modular design. That means, what do we mean by modular design? That this part I have to design in this way. So I can give the instruction, those who are working, this is the model of this design. People cannot actually speculate and cannot always do some design. So that's why the instrumentation engineers or these measurement people, if you have seen that, you have seen an instrumentation we divided with a functional block diagram. So you can think of the first one is the sensor, then signal processing circuit, then signal transmission, then there is a signal display. So we can say the instrument has, we have divided in different parts, and we will be working on the sensor, primary sensor, signal conditioning circuit. That means that is a modular design. That a small component, a small block wise I will design, then I will assemble, and then I will integrate. Because in our class also, when people start working with the circuits, what we say, we don't make the circuit at a time. You make one part of the circuit, check it, that what should be this input, what should be the output. If it is coming okay, then go to the next part of the circuit. Because if you make a big circuit and then it's not working, it is very difficult for you to debug where is the problem. So in the design also, that we have to adopt, that modular wise we have to proceed. Then use of standard components. Suddenly I cannot say, actually we, the IIT students, we have seen this is a problem. If we say that this is available, you build some instrument with this, they think because this is not very, if it is available, then what I will do by using this. Actually our society have boosted the IIT people so much that they think that if someone has developed something, I should not use that, and I, with my with my so much of intelligence and all, I should go for designing new things. And that's why they don't actually, are very few of them actually land up with a actual product, because they don't follow this basic principle. If you have a standard components available in the market, always go for that, because behind making that standard component, more than 10 to 15 years research and development work has been invested. When some people conceptualize a design, and when it comes to the market, at least 10 to 15 years is required. So if you have a standard components, you should always go for that one. Don't always try to do that. I will innovate something and that is my contribution. That is a very stupid way of thinking. Then designing parts for multi-use, that means if I design a part, it will be of multiple use. And designing for ease of manufacturing, naturally I will design such that I can manufacture with a ease, and implement a uniform PDDM throughout the organization. PDDM is product design development methodology. That means whatever design methodology I am adopting for a particular component, we have to see that whether we can adopt it for all the components. So this principle I have to follow. You just cannot actually invent the wheel again and again and say that that is my contribution. This is again I am saying, because we actually Indians are very bad in engineering. Though all of us do the engineering, but we are really very bad in engineering because we don't follow the basic design principles. So what is the essential element of PDDM? That is product design and development methodology. That is, first is we have to do the specification development, then conceptual design phase we have to go through, then detailed design phase we have to do, then standard manufacturing process we have to develop, and we have to also do the material characterization. So first begins with the specification. That means what the customer want, that we have to understand if we are going to design. So let me go with the example. Suppose this is an capacitive accelerometer, and I'll just give this example with the example of micro electromechanical system. You all know this is nothing but the accelerometer in the micron size. What is the micron size? Actually the mechanical sensing element. So as this is a most of the devices now use the MEMS sensors, so I'll just try to give the example from there. So you understand, this is the mechanical element, this is a capacitive element, this is we call the proof mass. So its physical schematic is here. So what happens here, if acceleration is applied, so this mass actually try to move up or down. If this is a vibration, then up down, or if it is only acceleration, it tries to move up or down. And actually this mass cannot float, right? So that mass has to be tied with some places, so or some point which we call the anchor points. So so by this mass with against some material we have to bind it, so that produces my spring, and that acts as an opposing force. If my proof mass is moving in this way, the spring force moves in the opposite way, that you know. And the damper is actually in which environment is this mass is there, proof mass is there. That means if it is in air, then I have some sort of damping. If it is in the oil, it has a different sort of damping. So these are the mechanical sensing element. Then we have the electronic circuit to get the output. So this is a very common circuit, charge amplifier circuit, because this is a capacitive element. This proof mass, if it moves up, this is a plate, the capacitance between these two plates becomes C plus del C, because C equal to epsilon 0 epsilon R A by D. So if my D is actually decreasing, capacitance is increasing, and here capacitance is decreasing. So that change in capacitance we can measure by this charge amplifier. Then we give a phase sensitive demodulator, and then we can give a low pass filter. This is available in many standard books, this set measurement, so you can look into this. So this is that I want to do a open loop accelerometer. I can also go for a closed loop accelerometer, but let us for today opt out that one. So now, as I was saying, that I want to make the structure. So how this structure, this I was talking about the proof mass, that means this one. And there is a plate, here is a plate. Now I said this you can think of a body. So it is actually somewhere it is fixed. This 4 point, they are fixed. So this elongated limbs, this actually produces this spring. And these are the lower plate, this is the upper plate, and if inside that is air, then I will get a different damping. If it is oil, I will get a different damping. If it is hermetically sealed, that is no air, no oil, nothing, then we should get ideally no damping, but still there is a damping. So this structure in a physical model we represent like this, right? So this is what we have to build. Actually, as a design engineer, we don't have to make this. This is for our analysis. What we have to make is this. So, what will be this design? MEMS design, sorry, it can be accelerometer design, I can say. That's a mechanical sensing element design. Then the electronic circuit design you have seen. Then integration of mechanical sensing element and electronic circuit, that is an issue. If you have a macro device, then you have a sensor like RTD, thermocouple, or what you do, you just that 2 port, you put in your some sort of circuit, and then you see that what is the temperature of a hot bath, or what is the temperature of any oil, or you can see that what is the pressure. So that you can do with your electronic circuit which you have developed. But here, if you have going for a MEMS, means micron domain, then that is 1 micron is thinner than our here. So that if my sensing element is so thin, then I have to think of that how I will actually integrate with that signal conditioning circuit which is available with me. If I can go for monolithic integration, that means the sensor and the VLSI circuit is very good, but that has also many problems. But then that is also comes under my design, that I will be integrated in the time of fabrication itself. Or what I can do, I can integrate the sensor, and then I can take 2 wires out or 3 wires out, whatever is required, and then I can design a signal conditioning circuit, what are the market available this electronic component, and go ahead. Then we have to think of that how we'll fabricate that structure. I have shown you this structure. Actually, this is the structure we want to fabricate. So in a macro design, it might have, you can think of a room. On the floor, you have put some metal plate, and on the roof you have put another metal plate, and from the 4 walls you have taken this some suppose steel plate, and in between you have put again a little bit thicker steel metal plate or some conductive metal plate. So what will happen if your room is actually getting some acceleration? So this middle, this will actually bend. This will, because it is fixed over here and this part tries to move, so it will bend and it will actually go closer to this one, or it will come closer to this one. So you have to, how you will fabricate this one. So in a macro domain, maybe in the lathe industry, so you can take a block, from there you can give the shape. But in the MEMS, you have to think of the fabrication, how you will fabricate such structure. And then packaging and testing, because it is a thin like a here. So how you will package it and how you will make it available for your testing, because so small thing, you don't know that whether the structure has come properly, whether there is any stiction has taken place, or whether the legs are broken. So that is also an designing issue. So in the mechanical domain design, what we have to first identify that what is the structural element need to be designed and what is the desired specification. So what do we understand by that one? To design a realistic process flow for the device, a solid model of the actual microstructure that is to be constructed using some CAD tools or FEM simulation. So this I want to give an emphasis that every design should have either analytical design or some numerical simulation, because you cannot just in the primitive ways people used to take a piece of wood or used to take some iron and try to make some tools. We are not in that era. Now we want to first see that what is actually will happen if I make such if I can fabricate such a sensor. So before fabricating, if I want to do that, then I have to go for simulation, and I have to use the CAD tools. So that I need to do, and then I have to do the optimization of the design, because any structure I need to do optimization, because if my length is more, then what will happen? If my width is more, then what is happen? Because what I want to do ultimately, the performance I want to optimize. That means someone was asking me what about sensitivity, precision, repeatability. So that performance criteria I want to fulfill. So every design, before making it, I have to go through all these design steps, and then we will be doing the fabrication and packaging and testing. That means when we are doing mechanical domain design, then also this packaging and testing, fabrication, everything I have to take into consideration. Just I cannot just think of that I'll just develop a mechanical thing, so why should I go for packaging and testing? No, because how much will be your size, how you are going to test it, that everything should come to your design steps. So that's why it is called the concurrent design. So then there are lots of specifications, many specifications. If you see first chapter, second chapter of any instrumentation or measurement books, so there are static specifications, there are dynamic specifications. But when starting as design, we have to actually identify the preliminary specifications. So what that means, which are the actually most important specification that I have to meet. So for an accelerometer, it may be the range. That means on what will be the G is the actually G for the acceleration. This is meter per second square. 9.81 is this value, right? So what will be its natural frequency of oscillation, how linear it is, and what will be its sensitivity. As I have given an example of a capacitive accelerometer, that means for every 1 G acceleration, whether it is greater than 1 picofarad, 2 picofarad, 10 picofarad. So these specifications I have to first performance specifications I have to first lay down. Then I have to go for designing that one. So you see the design equations we have to write. So all you know, this is a second order design equation. It is undergoing acceleration. So this mass is the m. So m x double dot is the acceleration. You know damper, that is b into x dot. This is the velocity, because we are doing a force balance on this proof mass. So on this proof mass, acceleration is moving in one direction, and this display proof mass is moving in one direction, but my relative displacement is moving downward. The spring is pulling it down, damper is pulling it down. So what is that force? This damper force is denoted by velocity, that's why v into x dot, and spring force is the spring constant into the displacement, that's why it is k into x. And what is the applied this acceleration? That is m y double dot. So if we write the second order equation, I think it is all known to you. This is, we can write xs by AIS is m divided by ms square plus bs plus k, or it can be written like this. So why I am telling this? We may know this is the analytical equation. We may solve this equation, but ultimately actually I have to go for designing this m. I have to go to design this k. I have to go to design this b. They all depend upon that this structure. That means if how much thick I have taken this one, how much length I have taken, that defines my m. How much length of this one, how much thickness of this one, that defines my spring constant. And what is inside air, or what is the gap, is there any hole in this, that defines my damping. So that means this equation, the parameters of the equations, actually that will be nothing but the variables of my this mechanical sensing element. So there may be some other design I can go for. That was shown a rectangular plate. This is fixed in this 4 points. I can have another design where I make a this is called the folded tether, and here actually this is being fixed with this substrate like this, and bottom of this what will happen, this is actually floating. There is a gap between this blue and this pink color. So if it is subject to some force, then this actually, this part, this is the folded part, and it is so thin that it will move this way if I apply force. So if there is a, everyone is actually a small comb are there, that means our fingers are there. So just below of every one of them, I can make different electrodes. They will work as my capacitive electrodes. So this is the proof mass. Previously this one my proof mass. Now I can go for another design where this is a proof mass. So what will be my mechanical sensing element design? That is also an issue, because that depends upon the fab lab I will be using, that depends upon the accuracy I want, that depends upon the non-linearity I want, every parameter. So between these two, if I compare very grossly, I can say the sensitivity of this mechanical element is more than this, but the natural frequency of this structure is more than this. Similarly, the cross-axis sensitivity, that means if acceleration comes from other direction, this will be less perturbed, or it will not bend in other direction, but it will be bend other direction. So here, if my sensitivity, I want to meet the sensitivity, I have to compromise with my natural frequency. So always design is that type of trade-off, because you cannot get something without paying somewhere. So here you are paying, you are gaining sensitivity, but you are paying for the natural frequency. So that's how we do these things. So there are many other mechanicals. So people have developed different accelerometer design. You can see if you look into the books. So if mechanical domain structure, so we, as already I have said, see, we have to list out that what are the different parameters which are actually affecting. So in this structure, this is mechanical spring constant will be defined by this length, width, and etc. In this structure, this will be defined by this length, width, thickness, etc. Displacement sensitivity, with the force it will move up and down. There is an electrode, there is an electrode. So how much with every acceleration it will displace, that will be my displace sensitivity. Here it will move this way. So if it moves, see, there are bottom electrodes and these are electrodes. So the top one actually moves and the bottom one is fixed. So how much it will actually move from its place, that gives my displacement sensitivity. Cross-axis sensitivity, already I told, suppose the acceleration, my desired direction is in this direction, application of force. But for some reason, if it comes from this direction, so what is my ideal condition? That it should not move, because I don't want to measure the acceleration from other direction. So, but what will happen, it will actually try to, because this is very thin, it will try to bend this way, a little bit angular way. And when it bends angular way, because these are capacitive fingers, they will be actually giving me different sensitivity and I'll get an output. But whereas here, if I acceleration comes from other direction, because this is a rigid structure, it will, the cross-axis sensitivity will be less. So similarly, many other specifications are there. Actually, time is running out. I'll try to finish in 5 minutes. So you can see, so we have to go for optimization of the design. So there actually, again, we have to take some help of some software, because again I repeat that if you are designing a sensor, do not try to build your own software for optimization, because some method people who has devoted 5-10 years to develop a optimization toolbox, so use that one. Using that optimization toolbox is no discredit. So only thing is that you have to optimize, so you have to formulate that nonlinear constant optimization. For this case, where I have to minimize the objective function, my objective function, that I want to minimize the area, I want to minimize the Brownian noise floor, or you forget about Brownian, thought of the noise, and I want to maximize the sensitivity. So that's why sensitivity is P I have written, so 1 by P. So we have to solve this objective function, and by using some design this optimization toolbox, and that will actually give me the different these values, that what will be the length of the spring, what will be the width of the spring, what will be the length of the central beam, what will be the length of the comb finger, what will be the width, what will be the how many numbers I will do. So actually you will get different values, and on the basis of these values, then you have to realize. So actually then you have to develop this one. So I think this much I just thought that I will be covering a lots of thing in designing, but that could not be done. So what I go to this slide, that in summary I would say the design for manufacturing of MEMS aims to develop the methods and associated computer tools necessary for concurrent engineering process of MEMS product, integrating consideration about manufacturing and assembly. The important points of this methodology are definition of systematic concurrent design principles, utilization of CAD framework, that means whatever software available, that is you have to take, and then you have to do the simulation, and then you have to systematically parametric modeling you have to done for volume manufacturing. So if we say that what is the design flow we should follow for a MEMS product, so you see first thing comes is the market input. That means how is the sales, marketing, reliability, quality, and then that also is related with the process input. That means development and manufacturing. So this go to the electronic design and this process, because whatever process available, that means if you have a lathe machine industry or if you have an VLSI industry, according to that actually you have to design. So that's why it is called the process input is what facility is available to you. So micro machine element design, we have to do electronic design, we have a package design, we have to do the integration and evaluation, and then manufacturing readiness. That means these are the flow chart we have to follow for designing. This I have said about the MEMS because I was going through a MEMS example, but the same thing we have to follow when we are designing for macro sensors as well. So I don't want to go to the other important issue of this ground planes. I want to conclude that we want to, when we are designing, so we do it for enhanced return on investment in process technology and reduce prototyping cycles, increase design and design efficiency. Of course, because the more efficient your design, it will be better effectively, or you will be manufactured it more effectively. And so of course the customer's requirement has to be met, and we also success and emergence of industry standards will attract participants, leading to growth. Until and unless these industry standards are met, we cannot attract people for procurement. So that's all. Thank you for your patience. I think I have exceeded time, so I can take some questions, though actually I could not cover
Yes,
the
ma'am.
whole presentation I thought of.
Hello.
Anyway,
Hello, madam.
I've got some idea.
Hello.
Excuse me, madam.
Hello. Hello, ma'am.
Excuse me, madam.
Oh,
Hello.
Can I have one question before?
carry on.
Yes.
Hello.
Hello, ma'am. Can you
Yes.
recommend some books for getting started with
design-
FEM simulations
For
for
FEM
designer?
simulation?
Yes, ma'am.
Okay.
Yes, ma'am.
Okay. So
Especially for multiphysics applications.
no, what you want? FEM
Means,
simulation,
ma'am,
MEMS, or what you want? That let me understand.
ma'am, actually, I'm asking some books name for
Why you
getting started with FEM simulations.
FEM simulations? FEM simulation, then I think there is an ANSYS data book. Okay. Now, see, what I was saying, that you cannot actually write your own ANSYS code for simulation, right? So what you have to do, you have to take a software where you have to do simulation. Now in the market, there are, for FEM simulation, different softwares are available. So for multiphysics, the ANSYS is good. Okay, there is Coventer wire is also good. So whatever software is available to you, so on that software actually they have a help this file, or they have a data book with them. When you, if you have purchased a software or something, they provide you the help files and these data sheets, so you can go through that and start simulation. Even you can do simulation in MATLAB as well. Okay, so
Excuse me, madam.
Okay, ma'am.
yes,
Excuse me, madam.
yes,
Madam, for design aspect, can the lifetime of the sensor is treated as a parameter?
yes, I
Lifetime.
think, yes, of course.
Hmm.
I have shown na lifetime. In
Hmm.
you see in one of the slide, maybe I have not give the emphasis, but automotive sensors lifetime is the one of the very basic parameters, because if you have bought a car and if every 1 year you have to change some sensor, that is not desirable. So lifetime is a very important parameter for automotive sensors. At least we want to make a sensor which has at least 5 to 10 years lifetime. But maybe in chemical industry, I am happy if it is a 1 year lifetime.
So one you are discussing about the acceleration
So
sensor.
lifetime is a very important this specification, and especially for automotive or what is a machine building industry.
Yeah. So in case of vibration sensor and acceleration sensor,
Hmm.
in that case, the control and also damping,
Hmm.
the is there is any relationship should be maintained while designing such type of sensor, the controlling torque and damping torque, how much what is the relationship between these two?
See, this if you want to make the structure, then you have to write the equation. So I have shown the basic equation, force balance equation. Okay, now if you say the torque, you want to read the relationship. So when I can go to my slide. So suppose one of the slide I just in this, you see, this is the displacement. I want displacement in this direction, but I want to avoid displacement in this direction. So what is people, the MEMS designer do? Suppose this thickness is actually 1 micrometer, but here they make a little bit more thickness, 2 micrometer, 3 micrometer. So what happens if it does, then actually the cross axis, the torque is actually reduces. And of course, for this structure, if you can write an analytical equation between the torque and this displacement, torque and the force applied, that will give you. But the problem is, when this is a complicated structure, then solving the analytical equation is a difficulty, because you cannot, for how we solve a differential equation, we write down some differential equation, then we give the boundary conditions. The boundary conditions may be the length, this etc, which is fixed. Then we try to get the unknown values, right? So now when I have a complex structure, then getting this out by analytical solution is a problem. That's why this finite element method or some sort of numerical methods is being taken. But it has been found that by that simulation, you can see that if you this is called the task width. So if you actually increase this one, then your torque actually reduces. So of course there is a relation, and everything if you have this type of structure, you may write the analytical equation, because whether it will move in this direction or rotate in this direction, that with the force you can always write down the equation, you can solve. It is not a problem.
Okay, thank you, madam. Thank you.
So doing analytical, do it if you can do it analytically, that is best, because that is a closed form solution we get. But when we go for the numerical solution, we have to choose. That's why we do the optimization and others thing.
Okay, thank you.
Hello.
Yes, any more question?
Yes, ma'am. One question. What are the various manufacturing or fabrication processes which we use for MEMS?
Okay.
Hello.
What is your question?
Ma'am, what are the various fabrication techniques or the manufacturing processes which are used for developing this MEMS?
Actually, there are three fabrication process, that is called bulk micromachining, surface micromachining, liga process. Now, bulk micromachining, liga process is not very much used. In some part of Germany, people uses that one. But for bulk and surface, that depends upon the what type of specification you want. If you want very high resolution, someone was asking for it, then actually you should go adopt a bulk micromachining, because then you can get a bigger mass. And in surface micromachining, actually you have a layer by layer you have to develop. So developing a thick mass is a problem. Now if you see this equation, so you will see that yes, here our sensitivity is 1 by omega n square, or rather sensitivity is actually it is actually, it will come m by k. If you just this omega n, if you just write sensitivity, so it will come m by k. So if your mass is more and your spring constant is less, then your sensitivity will be more. So if you want your mass more, you need a thicker structure. Now by surface micromachining, it is very difficult to get thicker structure, because it does layer by layer, and getting a 5 micron, 6 micron structure is also a problem. So that time you should go for a bulk micromachining. But if you are looking for a wide range, that means you want that my flexure will actually deflect more with a small force or acceleration, then you should go for this surface micromachining, because you can then make the structure this is actually made by bulk, and this is by surface. Then actually you can make this thin, and the more thin you make, with the less force it will deflect more. Okay, so there are three micromachining process, that is bulk, surface and liga. So again, that's why actually your in your concurrent design procedure, so what is the available of your fabrication or fab lab facility, on the basis of that also you have to design.
Okay, ma'am. Thank you.
Yes, any more question?
One again for the same thing. If we just see the future scope for MEMS as a benchmark to the NEMS, because both are in the development stage. We are developing MEMS as well as NEMS. So what can be the future scope of MES? Whether we are totally shifting ourselves towards the NEMS, or both will be in use in the future?
See, with the increase of MEMS, our macro sensor did not become obsolete, right? So in a names we are trying to design, you see names is 10 to the power minus 9, right? So that is actually very close to the Armstrong, and there what is happening, the some principle of operation gets changed or enhanced, as we have seen from the macro macro to micro when we have gone, so some more designing consideration we have to adapt, and we are getting some advantages. So I don't think that with the advancement with the names will become obsolete. No. As far as I understand, that it won't get obsolete.
Okay, okay, ma'am. Thank you. Thanks a lot.
Any more question?
Okay, ma'am. I think there is no more question from the participant side. So, thank you, ma'am. The presentation and the talk was very informative. Anyway, we are running out of time, so
Yes.
we must be leaving for our lunch break. So,
Yes.
okay, ma'am. Thank you. Thank
Okay,
you.
thank you. I can.
Okay, and to all the
Someone
participants,
was
we
saying.
will. Hello.
Hello.
Yes.
Hello. To the participants, I would like to inform that we will cater here again at 2:45 p.m. From 3 p.m. onwards, the session will start on basics of MEMS and NEMS, where you will be getting informations and other scopes of MEMS and NEMS sensor also. The session will be taken by Dr. Vasudeva Behra from NIT Jamshedpur. He is our faculty over here. So with this, we can move on for our lunch break, and I hope everyone will be there by 2:45 p.m. With this link only.